So this section is about neurotechnology revolution and ethical aspects on this neurotechnology revolution. I'm Mikael Sandlund, I'm a psychiatrist, and as a psychiatrist you also are a skeptic. So my first question will be, is this really a revolution? I mean, in the history of medicine, and not least in the history of psychiatry, there has been one or two revolutions which not has proved to be important to people's health. On the contrary, so you can't be sure. And the first speaker, I think, his task is to convince us that this really is a revolution which will be gainful for people suffering from mental disorders and lots of other disorders as well. He is a professor of physiology, I think, and head of the interdisciplinary Neuronano Research and Innovation Center in Lund. And then Jens Schouenborg is his name, and I will shortly welcome you to the stage, but also mention that when Jens has been speaking for about 30 minutes, we have comments from Professor Aldo Faisal, who is a AI professor. He's already told us, but he is also a unique person in many ways. Among others, that he is the first computer scientist to be appointed to the German Ethics Council. And Sarah Cunningham-Burley, who is, as she has already told us, the chairperson of Nuffield Council on Bioethics, and also a professor of medical and family sociology at University of Edinburgh. But please, Jens, the floor is yours. Let's convince us about this revolution. Thank you.
Okay, thank you for that introduction. Yeah, and thank you for inviting me to this meeting. It's really such an honor, unexpectedly big honor, actually. Thank you. Yeah, somebody persuaded me that this was not necessary, but I don't know. Anyway, I'll give you a little bit of a background to this field, and also about what we ourselves have been doing for 2 decades or so. So neurotechnology, what I'm going to talk about basically is implantable technology, whereby one can understand the brain and also treat brain disorders. So it's not in any way a new area. We have many established neurotech in the medicine, and I just mention the most principal ones. It started, I would say, with cochlear implants, helping deaf people to actually hear. There was a big ethical debate around it, but now it's established. We have deep brain stimulation, started in the 90s, one can say. Some start in 80s also. It's established and has helped numerous of Parkinson patients as of today. We have spinal cord stimulation for pain treatment, gallbladder control, peripheral nerve stimulation, implantable, and so forth. So it's not a new field. There's been a growing interest in what can be made or done in the future here, and we started our project in 2006. And the real reason for starting it was we needed better tools for science than was present to understand fundamental brain mechanisms. But we also saw the need, of course, in better tools for clinic. So in 2013, Obama started this brain initiative. And also very famous nowadays is that Elon Musk started his company Neuralink, trying to interface the brain. And that started a huge interest in the field, I would say. So there is a lot of potential in the field. I list a few here, but we have a lot of brain disorders, and they cannot be treated today. And so there's a lot of suffering going on, helpless people having their lives ruined. So there's a big need for doing something. There is a need for neuroprosthesis in disabled patients, and there will also be a need for drug delivery, etc., cell therapy, perhaps. So this side is an important side as far as I can see. So more recently, the interest has sort of skyrocketed, and that's because of not only Elon Musk, the richest man in the world, but also other very, very rich people join into this now. So, for instance, Jeff Bezos and Bill Gates, they invest in a company called Synchron, which is a neural interface technology. I'll come to a little bit about it. Mark Zuckerberg, yeah, you know him. He's also involved in brain-computer interfaces, non-invasive. Sam Altman recently, the head of OpenAI, starting or investigating equal amount of money as Elon Musk has done in a company called Merge. And very, very recently, China steps in fully and making it a policy, a research policy of the nation with huge investment in this. They are going to be the leading country in 5 years, they say. Anyway. So what drives this hype? Well, I found this, I cited this from YouTube, Finance. It's all about AI, actually. The need to, the wish to control it, to make use of it, and to control markets, perhaps. But let us not be confused by that, because that is not the big thing, I would say. Oh, sorry. So that stirs up a lot of questions. Can we read the mind in people? In particular, if people don't want us to read the mind, can that be done? And I put the quotes there so you can look for yourself where this hype is going. But asking AI sort of itself, can you read the mind by a brain-computer interface? And the answer is no. It is not possible, unless the patient wants it. Then it's possible. So I'll give you a little bit overview. So what it's all about is that's implants put on the brain, in the brain, sometimes above the skull. They don't really work on this context. And then use that information from signals in the brain to control a computer, cursor, so you can start to play chess if you're disabled. Again, you can make the moves. You can control prosthesis, robotic arm. A lot of opportunities whereby you, by your thoughts in a way, can control external devices. And more recently, this year in particular, it's been successful to sort of train an AI to understand words that you want to convey. So then one is using electrodes on the cortex or in the cortex cerebrum. And the thing is here that's super important, I think, that is that in order to be able to do that, you need to train the eye and you need to train your brain. So you need to sort of, it's not about mind reading. You have to sort of train eye so that you can control it and make words. It's not reading thoughts. So it's actually a one-way direction. You train an eye so that it can catch the words you try to say. And it works quite well, actually. But don't forget, it's not eye that is listening to your thoughts. What is actually transferred here is just commands. Motor commands. It's not thoughts. So that can be easily done, actually, if you record from muscles. And you wouldn't think that is a thought. It's the same thing here. You read, actually, the command to the muscles. And you have to train your brain so you sort of you narrow down the neurons that should be active when you say a word, right? So you have to train it. It's not reading a mind. I've said in another context that there's no way you can actually read a person's mind unless the person is willing to consent to do this. And why? Well, what is forgotten perhaps is that we are very different. All human brains are unique. And that means, and all the connections have been molded by years and years of experience. Interrogations with external world is super important for our brain to develop eventually. And that is always the different in different humans, right? So we all end up with different brains. We think differently. And there's no way you can sort of find a neuron that, let's say, think about the house or the car or whatever. If you can't do it because we are unique. So what's coming now is a lot of new technology, flexible electrodes with many contacts that are sort of robotically inserted into the brain in Neuralink. We have this type of stent-like electrodes which are inserted through the veins and channeled to veins overlying motor cortex in the brain. And they are actually able to also be used for this speech thing I talked about. They're not in any way ideal. It will be very difficult to remove this one, for instance. So it's tested basically in terminally ill ALS patients, where it has a place, I think. So our vision then, that was to develop neuroelectronic interfaces for potent treatment of brain disorders and also to decipher how the brain functions, to understand the brain. That's actually the biggest challenge we can have. That's to understand how the brain works and how we work, how we think, what's consciousness and so forth. We realized when we started in 2006, this is ethics is super important in this. And so within our group, we worked a lot on ethics and did our own research. We didn't put the questions, we didn't focus on medical risks, that is risk of injury, risk of bleeding or infection, which is the traditional risk that you think about. Let's say that we solve all these things. There are no medical risks. What then? What else are there? And we focused on deep brain stimulation and depression to see if there was any problem with authenticity. That is, will this be a problem for how your personality works? Can it change your personality? And yes, of course it can. If you're a depressed person and becomes non-depressed, you are changed a bit, right? But the issues, the ethical concerns are identical, we found, to those using psychopharmaca. You have the same problem there. It will change you. So it's not a new ethical issue. We didn't find anyone, actually. There is a difference. You can always turn it off. You can't do that so easily with a psychopharmaca. There's another one. It can be super precise, as I will show you. So other things we've been talking about already, and I have been talking about, is can you eavesdrop your mind and so on, and can you hijack the brain? We looked into all of these things and realized that this is science fiction thing, and will continue to be there. Now, how can I be so sure about this? Well, I'll go through a little bit of brain facts with you. Firstly, our brain has quite a lot of neurons. The recent count is like 87 billion neurons, and we have a lot of other cells there as well that interact with these neurons. And the number of connections between them is staggering. It's at least 1,000 more, I would say, much more than that. So an enormous network. Imagine that you would like to listen to this, signals in this system, by anything intrusive. There is not a space for it. That's the first thing. You can't put it in there. You will only be able to listen to a few of these ones. And the problem was really that the technology didn't allow us that either, because the technology, when we started, was so bad that you actually destroyed the things you wanted to look at. The brain has an anatomy, and so different regions have different roles. So this is also something one can think about when thinking about what techniques can be used for. We have areas which are important for motor planning, motor programs, vision, hearing, language, planning in the future, and all sorts of things. It's all at different places, but it interacts a lot. Now, this is gross anatomy. That's about what you see in MRI today. You can see how areas lights up, that the blood flow increases when you think about something or do something. But this is a level of where we are clinically speaking. It's MRI dependent view. But if one go deeper and look into the brain. So starting with that little square down to the left and then blow it one little part up, you will see these gyrus and so on, white and gray matter, and then go into a section of such a brain area, and you see numerous of these neurons. So under MRI pictures, we have the real brain, the real networks, and they are not visible today using imaging. Another thing in this little lecture is about how do they communicate, these neurons? Well, they send electrical signals. It's not like what you have when in a computer. These signals are special. It's kind of propagating potential wave along the membranes to the synapse, where chemical substances are released, and then the next neuron will react on that. So the language of the brain, that's electric language. It's electrons. So I think this explains a little bit why it's perhaps not an issue to read your mind with the new technology. The real key challenges in the field are, as we found it, these three. Firstly, when you put something into your body, you get a foreign body reaction that encapsulates it. That protects your body from the intrusive thing. And it happens also in the brain, and it was felt like a dogma before. Another big issue is that signals are going down and you just end up with noise. And the third one was in the therapy situation that there's a lot of side effects. So we focused a lot on foreign body reaction to understand it, understand the mechanisms, whereby you get it. It's about the same as if you get a stick in your finger and you leave it there, you will have inflammation and eventually encapsulation. It's not very difficult to know what I mean. And it happens the same in the brain. And eventually, if you have an electrode, you want to listen to a neuron, there is a barrier between the neuron and the electrode, so you don't hear anything. It goes very, very quick. So this is from animal experiments where one can see that structural changes of microglia, which is a part of the immune system, how it will react to a little lesion in the middle there. You can see within 10 minutes it goes in and enwrap. So we looked a lot on this. I will not go very much technical on this, but we looked into what is driving these effects. And yeah, did a systematic research for a decade to understand this. One example was putting an electrode probe either in one position or in the other. So either it can swing with the movements of the brain relative to the skull, or it cannot. And we saw big difference, right? So to summarize what we did, there were actually only two factors that are important. One is how you do your insertion, that you don't injure the brain, or you do it minimally. And the other is about the thing you put there must be compliant with the movements of the brain. So about that, whenever you sort of breathe, or the heart is pumping, there is a movement in the tissue. And so if you want to have a stable contact with what's signaling there, you have to have very flexible electrodes that can follow these movements. So our vision was in the beginning, it must be like seaweed, smoothly moving in the sea, but being stable relative to the sea. And we developed seaweed electrodes. Let me see. Like this, some 12 years ago now. We had it on exhibition at Science Museum in London. It's quite a fun experience, actually. These were gold, very, very thin, micrometer thick. So how do you implant these with precision? Well, we invented then, we invented techniques whereby we could embed it in gelatin and dry. When dry, it's hard, so you can go in and then dissolves and you have it in. We have developed this technique much more since then. And today we have electrodes that leave basically no imprint, no effect on tissue at all. There's no foreign body reaction, no loss of neurons, no inflammation. And with that kind of technique, so all of these green ones, by the way, are neurons. And in the middle, in the center of that ring, you have our electrode. And you can see the neurons are plenty just around it, just at micrometer distances. With that, we can see fantastic recording. We get fantastic recordings. I would say for the first time from an authentic brain. So to talk a little bit more about therapy then, and I will talk about brain stimulation basically. Today we have deep brain stimulation, and it works like you put an electrode of the type here in the middle, and into a certain area deep into the brain. It's connected with a wire to a stimulator under your chest. And as you can see, it's millimeter size. It's appears very little, but if you remember my pictures, you see it also next year, how detailed the organization is. It's too big for a brain. And actually, in one DBS electrode of today, you can have, that equals a volume of around 2 million neurons. So you can understand why that cannot be very specific. There are many problems. It's very helpful for many patients today. I don't say anything about that. But they're not scaled to the brain, and therefore there are side effects and there are problems with sufficient efficacy. So what have we been up to? Well, we have invented our new techniques that you can see here, which means a cluster of electrodes are inserted into the brain, and then we select out which are good ones and which are not good ones. Since they are highly biocompatible, they don't leave a trace, they can just be there. So eventually, scanning a field of many spatially separate sites, we managed in all animal experiments so far to select out those that block the symptoms that we are looking at. And not using those that produce side effects, we have a very clean effect. So the difference between a DBS of today and our is that we select the ones that produce positive effect, and we don't use the other ones. It's like if you have a medicine, and it spreads all over the body, you sort of can switch off the medicine in the other parts of the body to get rid of the side effects. This is basically what we do locally here. So this is a probe. It's not, perhaps I can say, the latest, but it's what we have been testing. So it's a system whereby we can channel out these microelectrodes, highly exact, precisely, spread them out, and leave, in the end, only the electrodes, super thin and flexible, moving like seaweed in the brain. And we are now about to send in our clinical application to be able to test this on Monday, I think. We have a lot of evidence. I just got the sign. We have done many thesis works on pain and on Parkinson models. And in pain, we were able to completely shut down pain in the animals with no visible side effects, no other side effects. We really looked for them. But it was very clean. So here are areas in the periaqueductal gray, it's part of a brainstem, where each of these yellow one is where we have had one cluster. And interestingly enough, since we don't end up with exactly the same position in different animals, we could always do this thing of selection and get the pure effect. So we have checked a lot of things to be able to actually move it into clinic, and the most important is, of course, the biocompatibility. We focused on, you can't see them, unfortunately, but there are some spots here that you can see where we've been with the electrodes, and we focus in on to try to get rid of those small things. But in reality, if you compare, this is the size of a normal DBS. It would crush all of that. And the foreign body reaction would take up that space. So we are like thousands of times better in biocompatibility than today's technology. So to sum up, what we have been doing is to minimize the foreign body reaction, and that provided us with fantastic recordings, stable over 6 months in rats, which is a fourth of its lifetime. And we have seen very powerful therapy, and we are able to minimize or actually eliminate, as far as we can see, the side effects. So thanks for listening. This is my team. There are 2 more has been recruited, actually, but yeah. So thank you.
Well, thank you so much. You can step down, and then in the end of this session we have a general discussion. So now, Aldo, Faisal, please, can you answer the second question? Well, we are now convinced this is a revolution. It will be very beneficial, but are there any ethical issues left which you didn't solve in 2010 when you looked through every problem then you could discover at this point of time? Please.
Thank you very much, and also from me, happy birthday, Smear. It's fantastic to be at this event, and thank you very much for a very clear introduction to the topic. So I'm a member of the German Ethics Council, and as usual, I give my standard preamble. Most of you will be familiar with it. When I'm speaking about this, I'm going to speak from my own personal perspective as a scientist. The German Ethics Council has worked over the past few years on the topic. It started right at the start in 2009, where they had an annual conference on human dignity. In 2013, they entered into the topic of neuroimaging, and there was a question about decoding brain information. In 2018, we had an annual meeting on human rights, where human rights about your brain and interfering with your brain came up. And then in 2021, we had a statement around artificial intelligence, where also the element of neurotechnology appeared. So roughly all 4 to 5 years, the German Ethics Council revisits the topic, but what we've never done before was have a proper statement. You know, this is these big, heavy reports, heavier than most bags these days, of 80+ pages of detailed work. And in 2025, we decided to embark on that journey. So, as with everything in the Council, nothing is final till it has been approved by consensus by the Council and published. So, all the views I can give you is my own views, plus the evidence that you can see from the public hearing we held on neurotechnology last month. So I don't need to give you an introduction to the neuroscience of neurotechnology, but I wanted to frame it a bit. If you look at the billionaires on this planet funding neurotechnology and thereby generating public interest just because they're interested in it, you see that Elon Musk publicly states that the reason why we need neurotechnology is to render humanity competitive with artificial intelligence. So for him, it's almost a survival question, just like we need to colonize Mars. For Mark Zuckerberg, again, the idea and vision that he and his company have is to enable persistent, instantaneous interaction between peoples, preferably through his own platforms. And so we have pathways that are basically driving the public interest in this domain that are very different from how we used to innovate in neurotechnology. Typically, neurotechnological innovation was driven like nuclear innovation, like biotechnological innovation, through innovation that happened ultimately through government funding of one form or another and was just tightly government controlled. What we've seen now with the end of the 2010s and the start of basically big tech Silicon Valley moving in is that we're seeing companies driving the innovation, putting very substantial investments into there that exceeded by now what Obama put at the time into the BRAIN initiative, and are now driving things from a very different perspective. While maybe before there was a medical device and helping people who are paralyzed or have lost some form of function of their brain and their nervous system, now we're talking about consumer technologies. And with that is always implied the shift from tightly regulated medical devices to consumer gadgets and toys. And the difference is, just to remind you, as big as being, getting approval for a new pharmaceutical product or buying nutritional supplements. So what is happening here in this space? Well, on the one side, we're seeing now that these technologies are being driven by products that are coming onto the market already at a very fast pace, just like ChatGPT for some suddenly appeared in 2023 and changed their perception and use of AI technologies. And so this sudden acceleration means that our standard pipeline of there's science, there's a vision, in the far future we'll be able to do that, ethicists pick up on that, that informs then policy and law, and that then drives regulation and standardization. You know, it's a nice pace. If you have 10, 15 years of time, it's now dramatically compressed. And now we're suddenly in a space where Well, ethics, regulation, policy, law sort of happen in parallel, but mostly trying to reactively catch up with products being released. And that's possible because of the shift of how the funding landscape is controlled. So on the one side, we need to catch up, and on the other side, we need to help drive these things. So let's take back from this global framing to some of the questions we've been thinking about. And so one of my teachers, Daniel Wolpert, once asked me, Aldo, why do we have brains? And he had a very specific answer in mind, and that answer is the only reason why we have brains is because we need to move. In fact, all organisms on this planet that don't move don't have a brain, and some organisms that can move do have a brain. And he had always this beautiful example of something called a sea squirt, which is a little animal that swims in the ocean, attaches to a coral, and then never leaves the coral again. And the moment that animal does that, it does the first thing, it starts digesting its own nervous system because it's not moving anymore. And that's often what happens with bright-ranked scientists when they become professors. So in this setting, neuroscience and thus also neurotechnology is ultimately about making actions and making decisions. The only way our brain can interact with the world is by doing something, and the only way we know that your brain is something because you're doing something, be it to eat, to talk, to walk, and to speak. And so this means for us, or for me in this case, the view of neurotechnology is broader than just the hunt for neural signals. It's not just about electrodes in the brain, and we're going to talk about that. It's also what you can decode non-invasively by going into the surface and still capturing neural signals. And here we have interesting results, especially in the non-invasive space, where you have functional infrared spectroscopy that generates a signal that is very similar to MRI signals, but there's some interesting inequalities. If you have black hair or dark skin, this infrared signal that penetrates the skull is not so well decodable. So you suddenly have inequalities in the accessibilities. And if you're at an institution that has a lot of students from China, for example, it's near impossible to recruit sufficient subjects to do studies in that domain because of these ethnic components in the brain signal that is being absorbed. So there are inequalities arising because of this. But also, and you could see that in our public hearing, we had evidence of how far you can push if you integrate just sufficient levels of different sensor technologies, not just that you put on your brain, where you can argue that a user can take off the technology just like I can take off my glasses and be free from it, but how much can be now detected from ambient technology. And if we go back to the statement, why do we have brains? It's to make actions and decisions. If we can start predicting every single action that you make without necessarily requiring a brain signal, what does this tell me about the privacy of my thoughts that lead to action? Right? And so there's a broadening that we're seeing, and major interests in this space are about exactly enhancing this ambient intelligence to help predict technologies in that domain. And then we saw examples from colleagues in Stanford at our public hearing that showed us how you can now transcribe thought speech, where you're thinking about speaking something, and verbalize that. And there's been promises, not just in the invasive space, but also some early results with non-invasive brain recording technologies. But I think there's more to that space than just the technological, biological innovation. What also became clear to us is that there's also, because the space is being rapidly developing, we're talking now about parallel ethics, regulation, policy, law, and certification of such devices, that we maybe have to start thinking about how regulation in itself is an ethical choice. And so the innovation of regulation in itself may impact how we need to think about that. And this is something we're typically not touching upon. We're touching about the technology and the science, but not how the way we govern that has ethical impacts. And there's another aspect, and this came up also earlier, and that's the aspect of self-experimentation. Right? Self-experimentation is fantastic. We can all play with that. Now, every school kid can do fantastic things with AI tools they can download. But if you see now the evidence of biohackers who start modifying their body, they can do that. You can do things to your own body if you want to. But that communities become so engaged now that, for example, in Switzerland, you can now visit a lab that is at the scale of a full-blown university lab. You pay something like 50 Swiss francs a month subscription, then you can go and start doing that. And where it becomes interesting is that these communities are starting to talk to each other, of course, and are helping each other modify each other. So that's something we've not considered so far. And I think it's very interesting to look at this aspect. So I want to come to a quick and early end here, is that I think this topic of neurotechnology, while it may seem like a topic we've heard about 20 years, has dramatically transformed. And it's ultimately dramatically transformed, as my previous speaker already said, by AI. But what that transformation means is also a fundamental shift in why we're doing that. Well, early neurotechnology was effectively a very good excuse to fund fundamentals of neuroscience to understand our brain. The shifts that AI has brought to science, that we want technology that works, even if I don't know why it works. A beautiful example is AlphaFold, that predicts the structure of proteins, awarded with the Nobel Prize not far from here last year. Gives us a tool that perfectly predicts what happens, but doesn't let us understand why it happens. We've not understood what makes secondary structures really fold. So this transformation is a shift from a scientific understanding and scientific explorability to things that work, and because they work, they're useful, and thus we can use them. And this is a more global challenge that we're going to face going forward in the future. Thank you.
Thank you so much. Well, I felt myself that something happened with the brain as I became a professor, but now as I'm about to retire, it might regenerate, or at least one can hope for that. Well, Sarah, thank you for your extremely exhaustive description. Well, what's about Nuffield Council and neurotechnology, please?
Thank you. Thank you very much. Delighted to be here. Happy birthday. It's been a great day so far as well, with interesting talks across the board. So the Nuffield Council on Bioethics, as many of you will know, conducts ethical analysis across a really wide range of issues. And we currently have 3 priority areas, one of which is mind and brain. So that's good, because that's why I'm up here on the platform. But that, by calling it mind and brain, we're also taking that kind of expansive view of what neurotechnology is, as Aldo has addressed. And I think that's very important. Issues to do with the mind speak fundamentally to our moral selves and to our values. And that framing, I think, can help us in terms of how we address, confront, and perhaps challenge some of the developments in relation to neurotechnology. So just for the next 10 minutes, or maybe less, I'm going to talk a little bit about our approach to the field now, and then talk about 2 areas of work that we are engaged in. One's completed and one is ongoing. So just in terms of introduction, as you've already heard, the Nuffield Council on Bioethics is trying to embed ethics in horizon scanning. So not only identifying what developments in science are going to come in the near and maybe more distant future, but what are the ethical issues, including shifts in societal values that will shape our relationship with those technologies. The National Institute for Health Research in the UK has conducted its horizon scanning of innovative or upcoming technologies, and in 2025, this year, it identified 81 unique neurotechnologies, the majority of which, 63, are non-invasive. So that really is the field that we need to be beginning to address and ask questions about. In 2013, the Nuffield Council on Bioethics before my deep engagement with the Council, wrote a report and provided an ethical framework on novel neurotechnologies. And as we were coming back into this space to see what we could deliver, what we could do that was make a distinctive contribution useful to us all, we went back to that report and decided to sort of revisit and explore what had changed over that time. And one of the significant changes was this growth in non-invasive technologies. Some of the key themes that have come out of our kind of re-engagement in this space is that the pace of research and development itself is generative of problems in relation to regulation and oversight. So our existing taxonomies in relation to that are useful for governance at the moment really do challenge that governance framework. So in the UK, generally, the more invasive a device is, the more stringent the regulation. The less invasive, then the much more flexible regulation or very little regulation at all. So invasiveness maybe is not the right differentiator now in terms of our regulatory response to those developments. It's very easy for non-invasive devices, as Aldo has said, to be marketed direct to consumer. And that raises questions of potential for harm in the absence of clinical oversight and advice. The other issues that have come out of our preliminary review in the space will be ones that will be familiar, I think, to us all. So issues around equity, but both equity at the stage of development and design of technologies and equity of access. And of course, the political economic framework within that provides some of the drivers for these technologies also demand an ethical lens. So on development and design, we need to really ask whether the data that drive some of these developments are truly inclusive across populations, for example. And we also need to ask at the point of implementation, are there barriers in terms of equity of access? But that's assuming, of course, that one should be implementing some of these technological developments in clinical or non-clinical settings. There are also impacts on identity, both at an individual level, but I think really importantly, and speaks to some of the points made earlier this morning around kind of community and group identity. So there may be impacts on individual identity if there are issues around memory modification, for example, and also issues around kind of the normalization of neurotech might impact the ways in which we manage our moral lives. And community identity, there are concerns around erasure in terms of different disability communities, and also some have written about neurotech potentially being an instrument of neo-colonialism. If neurotechnological progress continues to be pitched as universalist, but is based on Western identification of problems and solutions and data from Western populations, then we are delegitimizing or not even taking into account very different worldviews of the relationship between mind and brain, mind and human and non-human activity. And another area that came out of our review is the issue of obsolescence. So this wasn't a consideration when we published our work in 2013, as neurotech was so novel, but we've now identified that concern about the loss of function and possible harm when support is withdrawn for devices or support becomes obsolete. I mean, we know how often we have to update our phones, for example, so that requires a kind of constant engagement and constant resourcing. And if that resourcing goes, and particularly if developments are created by startups that may themselves disintegrate or be taken over by larger commercial entities. So issues of obsolescence are ones that also demand our attention. Of course, and I won't go into this now, issues around privacy and consent remain incredibly important in this field. We've heard a little about consent in this context and also about privacy. So that's, in a sense, providing a very, very broad lens of what we might need to focus on as we move forward in this field. The next step for the Nuffield Council on Bioethics is to identify where we feel we can make a difference and that the work that we would do would then gain traction. So that's always a challenge, I think, probably for all of our work. And sometimes we take a deep dive into a very specific area, but also use that deep dive to somehow kind of explode or make visible some of the bigger picture. And the very first piece of work that we have done in our current strategy period, which is 2024 plus 5, 29, has been on neural organoids. So when I heard Jens and your 87 loads and loads of noughts nerve cells, I think it was, so what is the problem with neural organoids? There's not going to be that many cells in an organoid. But why do we need to pay attention to this development in science? As part of our horizon scanning, it's an area that is under rapid development. But also importantly, those engaged in the science have engaged with us and are concerned about regulatory gaps, concerned about what they're doing, and that there are kind of ethical issues embedded in what they're doing, which they want to surface, discuss with us, and get advice on. So it isn't simply that the Nuffield Council on Bioethics or any other ethics body are saying, oh, there's ethical issues here. These are real and felt in everyday experience by scientists, and I think that's very important that we kind of co-produce any outcomes in terms of future regulation and ethical frameworks in this field. So neural organoids, for those who don't know, are small lab-grown three-dimensional structures derived from stem cells, and we focus particularly on those derived from human stem cells. And the idea is they can model different aspects of the brain. They'd be very important in terms of fundamental research. But research is moving at pace, and there are potential applications, particularly in terms of treatments. However, the research is at a very early stage, but that doesn't mean we shouldn't be debating some of the ethical issues here. They may be useful for modelling conditions, for modelling neurodevelopment, and also for drug testing. But we're asking ourselves, do we need more tailored ethical guidance and oversight in this space? And there might be several reasons why we need this. Are the existing consent arrangements for tissue donors, so those that are donating stem cells, appropriate in this context for a technology that is novel, that may develop in ways that we do not yet know, and that may result at some point in something that could be implanted in terms of clinical use? And are we apprised enough? Are we making good enough assessments about the potential benefits and harms, both for humans as well as non-human animals, on whom much of this work will be tested? And the other question is around potentiality, I suppose. Is there a potential for these organoids to develop in sophistication and structure to become increasingly similar to human brains? And in which case, how do we characterize those entities? Do they raise issues of sentience and consciousness? And I'm sure there are arguments for and against that. And we will also have to keep readdressing those arguments as the technologies develop. So that was our first foray into this space. We now have a working group, and Stephen Wilkinson, who's here, is on that working group, so maybe able to answer questions better than me, looking at some of the ethical issues and relationship to regulatory issues that may derive from these consent processes. What would proportionate regulation look like, for example? So just very briefly, one more thing before we stop for questions. And this is quite a different area, excuse me, for the Nuffield Council on Bioethics and probably any bioethics body to focus on. But it comes within our appreciation of mind and brain. And this is to do with genomics, prediction, and education. So it's ethically contentious. It's bio because it's around genetics and genomics. So we have conducted a piece of work that has scoped this area of the development of polygenic risk scores that have some claim for relevance in an educational context. And this is using genome-wide association studies, identifying the multiple genomic and genetic markers that have some behavioral significance that may be correlated with educational outcomes. And the possibility raised by some scientists that these polygenic risk scores, these predictive scores, might help in an educational setting by identifying which children may benefit from which types of interventions to help level the playing field and produce equity in an education system. However, our work definitely revealed the massive uncertainty in that science, demanded us to ask the should question in terms of the history of behavioral genetics is far from robust. The existing data is very, very limited. And these many genes of small effects may have an interactive effect that might have some use may have some predictive values. But we also know that multiple environmental family factors are highly significant in an educational context, as is the educational context itself. And the potential for harms are great in this area in terms of stigma, profiling children with uncertain effects, if you cannot guarantee positive outcomes, for example. And issues of consent, agency, and privacy loom large in the context of genetic information, as we all know. So the results, we've got 2 reports based on this work, certainly recommend extreme caution in any development in this area, and also to be really transparent about the limits of the science in this space as well. So very, very different areas, kind of a broad brush, very specific on the neural organoid technology, and then also taking our kind of lens, I suppose, to another area that is, I think, increasingly relevant to bioethics and neurotechnology. So thank you very much.
Thank you very much. Please, Jens and Aldo, take your seats or your standpoints, at least. Any comments from you, Jens, after heard what they are doing in the ethic councils? Quite a broadening, I think, compared to what you do in your lab.
Well, we have the ethical perspective going all the time, actually. One thing I could say is that it's super important that you base your ethic discussions on the actual science and not the science fiction science. And because there is a lot of overtones, I think, in what you can do. And you can't, you know. So therefore one should be careful with which ethical questions one actually is concerned with. I have another little thing here about these brainoids. As I also said a little bit about, our brain is a result of a lifelong learning, and we are unique, all of us, for that reason. A brainoid has no experience with the world whatsoever and will never devolve into a normal brain. It's like looking at an extraterrestrial type of thing and thinking about ethics for them, in my mind.
Thank you. Any comments?
I think you're raising a really interesting challenge, and I think it's a challenge for us all, because on the one hand, we absolutely have to horizon scan, and we do have to think about the future, and the future is unknown. But we do know enough about the past and the present and the drivers of change to be able to predict with some certainty the directions of scientific developments. And science fiction now becomes non-science fiction in the future. So I think it's a boundary that's quite hard to sustain, although I completely take your point, and I hope at the Nuffield Council on Bioethics we engage very closely with the science community, so so the accuracy of our understanding of science, which certainly may not have come over in my presentation, is absolutely key to what we're doing. So and working with scientists and with policymakers as well as publics. But I think our future's thinking is evidence-based due to our emergent understanding of science as well as our understandings of the drivers of change.
I want to pick up what you said on the horizon scanning. I think it's clear things are moving so fast, we need to spend effort here. I think the challenges that I laid out was also the transformation of who does the innovation, who does the science. And something that I've not seen a lot in the past, but I think that we need to consider doing in the future, is not just talk to the scientists that sit in academic and public institution. We need to find a way of learning what happens in industry. And of course that is fraught with conflicts of interest and loads of other issues in that space. But we need to open the dialogue to understand what their vision is and if they have probed their vision sufficiently. And I think if we can open that dialogue and have that dialogue, I think we can at least complete the otherwise incomplete horizon of these rapid developments.
Thank you. Let's hear any questions from the audience. Henrik is delivering a mic.
Thank you, Professor of Practical Philosophy at Stockholm University. I can't help thinking in those science fiction terms, even if you resent that. I mean, you can help people with Parkinson to move in an ordinary way, and so it is interesting, of course, to know to what extent it will be possible to enhance our cognitive capacities. Take just one small aspect of intelligence, pitch. I suppose that's simply enough to, I mean, people vary here. Some have perfect pitch, others have lousy pitch. You're not ill because you have a poor pitch, but you could enjoy music in a way that you can't if you have a better pitch. So my first question is, do you think fairly soon that we will be able to help people with poor pitch up to normal levels? And the next question is, do you think that we should, as a society, have the ideal, the goal of biological egalitarianism? Should we level out cognitive functions and so up to a level where the best are right now? I think that's something for the council also to contemplate.
Thank you.
Is that the question to me now? Or? My personal view would be that the normal human brain is a beautiful construction, and I don't see the reason for going in. I don't see the ethics around it to try to enhance. I don't even see how it can be enhanced, to be honest. But if you have had a stroke, or in the elderly, your mental capacity is going down, and you have an option of restoring it. Yes, that's possible, and that I would think is also ethical.
But do you think it's impossible to be a perfect pitch?
What do you mean by perfect pitch?
I mean, you could hear a tone and say, this is an A.
Okay.
This is 440.
To help a person to actually hear that, you mean? Maybe. I can't really answer. I cannot really answer you because it's outside my sort of domain to. But if a perfect pitch is about contrast, let's say, maybe you could. But you could also sleep better and then hear better after that good sleep. So the question would be, can you do this better in normal ways? I don't know. But what I think will be possible is to restore some functions that are lost after stroke, let's say, or help the regeneration of the brain to become restored. That I'm sure about will be possible in the future. But about the other things, well, you can have hundreds like similar things to ask, but it will be very difficult to really answer that.
I think that the kind of boundary between restoring normality, so that's making better a pathology, versus enhancement, obviously is a very flexible boundary. That's why we have to look at it. I'm not going to answer that question, but biological egalitarianism, one, exactly what would it look like? Because the range of things in biology that are manifest in who we are is so vast. How could you even equalize? So there's that kind of possibility question, but that's really not what you're asking, is it? It's actually, should we even be thinking about kind of, let's say, raising the level of cognitive ability across populations through some kind of biological manipulation, as opposed to what we already do, a range of social engineering and educational initiatives to do that. I think we should, well, first of all, come at it partly with the harm question, and also what one would lose in terms of humanity if that were to be the case, in terms of diversity, difference, respect for all of those things would be partly my answer to that question. Aldo may have a much better answer to the question.
I doubt it, but I don't think neurotechnology is the way we will achieve more egalitarianism in one way or another. I think if you think about how we're defining intelligence and it's education and being refined and being able to write and speak and do mathematics and programming, well, I think what modern AI shows us, programming is one of the easiest automatable tasks. I thought it was the last job to go. It's the first job to go. And beautiful white-collar work is probably not so hard, actually, because an AI can do it, but no AI can fix your leaking tap at home. Right? So I think there's going to be a fundamental reevaluation of what is achievable by what technology can achieve and where our human limitations actually are. And so just like, this phone helps me remember things that I have limited capacity for, I think we're going to see a lot of this allegedly intelligent behavior like writing and text being improved globally across the board by people through AI technologies, where I think neurotechnology may help us, give us more skill in how we use our hands and how we move. You become a better dancer, better craftsman, or better artist. I think that's where I see the benefit of neurotechnology. Pitch is perception. I think the real enhancement comes through action.
Okay. More questions? I don't know we can start with Göran.
Thank you. I will not sing now. I just raise a question about the borderline between science and productions, which you mentioned, Aldo, Faisal, in your very interesting comment here. It's obviously already so, and in the future even more, that, for example, Elon Musk will be developing and put a lot of investment in this technology, which is related to this scientific advancements. Knowing also that Elon Musk is actively supporting the neo-fascist movement in Europe, it gives me a little scary perspective how these technologies can be used also politically, not only economically, but how they will be politically applied. So can you comment a little on that, please?
So I think ultimately we're talking about sovereignty over these technologies, be it sovereign AI or sovereign neurotechnology. Elon Musk himself ordered during a Ukrainian counterattack to shut off the Starlink internet services, which put the Ukrainian forces into a difficult situation. We had a US president order the shutdown of office services from a major provider to an international body, the International Criminal Court. So we're seeing that there's interference out of individuals being highly motivated and powerful that can enforce that. So in Germany, for example, the German government instituted something called the Cyber Agency, which is a combination of the German Defense Ministry and the German Internal Ministry, that specifically launched a major program on the safety of German brains. And so they were specifically looking and trying to evaluate how can we evaluate BCI technologies, that brain data is not exported at scale and cannot be exploited. And if you look at, for example, the recent advancement of Meta that they had on this new brain typewriter technology, they use 60,000 human neural activities to train the AI that built this model. And so it becomes an interesting question, who has access, who has governance control? It's not just governance about the data or the model or the technology, but who can actually choose when and how it is deployed. And I think here we will need to reorient ourselves. And I think it's very fortunate that we're in a community of, at the moment, mostly like-minded governments within Europe to be able to enforce that. And this is something we need to take much more into our approach. And that's the ethics of sovereignty, ultimately.
I think it's probably also the ethics of engagement too. So it's great you had your public discourse last week or very recently last month. So if we're thinking about kind of political use, other forms of dual use in terms of defence, if you can sort of, what's the word, attenuate empathy, if that may be very useful in the context of armed forces. And I think discussion of these, through public dialogue is also one way in which we can kind of intervene to shape the discourse and then raise questions around, who controls with what effects and how might one mitigate that in a way that creates a more positive future.
Okay, I think it's one last short question, I think. Please.
It actually follows the last question, and it's this question around who does the science. And I think the narrative at the moment is trust in science. Whether you take Caesars, it's not really about. But I think, Aldo, what you're saying in essence is there's a real difference going on here at the moment. The academic community has a belief that it's science for good, science for health, right? What's going on here is there's a community out there with the science for enhancement. It's not necessarily science for the better good of the community and the population. And I don't think publics differentiate between science being done for good now and science being done for enhancement of particular few individuals. And I wonder how you think we're going to have to deal with that, or national ethics committees, including the German ethics committees, are going to have to deal with that going forward, because to me it feels like a fundamental shift with new technology and who's in control of it, and dealing with the public. So yeah, how is Nuffield, how is the German Ethics Committee approaching this?
Yeah, we will hear two short answers on a rather big question. Please, Aldo, can you start? Or?
Sure, I can start with it. Again, I cannot speak for the council. Just my recommendations, I think we need to talk to industry, because we're not talking about science anymore. We're talking about product development, because the stage from basic science to product become very short. And we need to engage with them. And we then need to very proactively start thinking about how we actually want to regulate these things, if we have to regulate that. So regulatory innovation is part of the scientific and technological innovation, in my view.
Yeah, and I agree with that, and I would just add, so we also have to engage with social science. Obviously, I would say that as a social scientist, but actually because of our kind of perspective around biopolitics and political economy, that can help, even if we're focusing on quite a specific issue, that we always can broaden our lens to look at those wider drivers.
Okay, this will conclude this session. Thank you so much.